Hello there. I'm going to show you a project I've just finished to automate a ZWO filter wheel. This is a manual filter wheel, and we're going to turn it into an electronic version of it. And we're going to communicate to it from Ascom as well, so you can use it with Astronomy software. So this is the filter wheel. It's a ZWO filter wheel, or ZWO, I guess, if you're American. And it comes in two variants, which is the electronic filter wheel and the manual filter wheel. I've got the manual one, and I picked this up secondhand quite reasonably, but we're going to convert it into this with our own bit of electronics. It's not going to be as neat as that one, but it's a lot less than buying the electronic one. And here it is. So that's the box that I've printed in the 3D printer, a couple of little buttons to turn the filter wheel around, and the whole thing's driven by this stepper motor. That's a 28 BYJ48 5-volt stepper motor. So the wheel itself, as you'll see in a minute, has had a hole drilled in it where we've inserted a magnet, and we've got a Hall effect sensor in here, which will detect that magnet as the filter wheel rotates, and from that we can calculate how many steps it takes to rotate that filter wheel, and then find the positions of the filters themselves. I should say at this point that this is based entirely on a YouTube video that's already up there doing pretty much the same thing. And this is my interpretation of it, because there weren't any files associated with it. And I think in the case of the other video, which I will put up, he was communicating with when it was connected via Ascom, he was communicating with the ZWO Ascom driver. So this was interpreting the same codes that the ZWO driver was sending down to the hardware. So kind of a bit of backward engineering. I've written my own driver, so there's kind of no issues there, and I'll show you how that all works. So without connecting it to Ascom, we're just going to stick a 5-volt supply in there, and what it will do is it will go into calibration mode in the first instance, locate that magnet, rotate 360 degrees round the wheel to work out how many steps there is in a revolution, and then go to a filter position. So if I plug that in, and you'll see it immediately says finding magnet, and the wheel starts rotating. And we should see here the magnet coming into view any second now. There it is. So there's the magnet, and this will find the magnet. Oh, it's already found it, sorry, but it's finding it again to calculate the steps per revolution, and then going back into the filter wheel position. Once it's done that, we can just press one of these buttons, and you can see at the moment it says parked filter 4 brackets 4. So that's saying that it's in position 4, that's the bracket 4, and that filter is called filter 4, rather dully. And then we can press the minus to go back to filter 4. So filter 4 to filter 3. We're now in position 3 on filter 3. Or we can go plus and go back to filter 4, and so forth. So you can use it like that, but the really interesting part is to link this up to Ascom software and drive it from there, and I'll show you how to do that later on in this video. The idea here with the filter 0 bracket 0 is that we can in Ascom rename this, so if it'll still show as position 0, but it could be red or blue, green, IR, whatever you want to label it in Ascom, then your software will know it as that, and you can direct your software to go from red to blue, and if it's 2 slots apart, it'll jump one filter and go to 2 filters on, and so forth. And this will work out the shortest route. So it'll go clockwise or anti-clockwise depending on which filters you're going between. Okay, so let's have a look inside the box. I'll take that power supply off. we've got 3 bolts here. These 2 here replace the screws that were already on the filter wheel. So these screw down into the filter wheel itself. They need to be obviously the same dimension and thread. I think that I'll put the specs in off the top of my head. M3.5, I think these are. And you can see they're kind of like that. Allen key headed bolt. There's 2 there. And then we've got 1 bolt at the bottom here, which is a little bit, I guess, tricky. I made there's a recess in the bottom of this case to hold the hex nut, and I just calculated that a little bit, so it's a little bit, doesn't hold the nut, doesn't stop the nut from spinning. It's a little bit too wide. Anyway, so that's the bolt taken off, and then if we take that off, you can now see the components inside. So you've got the step motor here, you've got a 3D printed driver wheel on there, and on that wheel there's a rubber band. I just happen to have a suitable rubber band in a drawer. My partner says every rubber band we get from parcels, and lucky she does, because that was perfect. And we've got the circuit board here on a little bit of donut board, I think they call that, with the LED screen. I've kept the information on the LED screen pretty basic, like large font, basic. This is your filter on. You're on. This is where you're moving to and from. That's the way I like it, because it's nice and simple, easy to see. And what else do you need from a filter wheel? And then you've got buttons here, obviously, to go left and right that we were using before. That just sits on the top there, and you can see underneath we've got the cables going through to the stepper motor and to this Hall effect sensor here, which is the component that's detecting this neodymium magnet. I drilled a hole in the side, as it was the same design as the one that's already up on YouTube with a little magnet on the side. I recently bought a bunch of tools from an auction site, and amongst those were some center drills, which are kind of big, thick drills, and they're perfect for this. They drilled a really nice, neat hole for that magnet. Right, and then on the back of the board, you can see it there. You've got this microcontroller here. It's a, I don't know if you're going to be able to see that. It's a Arduino Arduino ZWO controller, and it's an Arduino type controller. And then we've got the stepper motor driver integrated circuit there, and not much else really. A few resistors. I think there's a capacitor there somewhere as well. Small capacitor there, and yeah, it's a pretty straightforward circuit, and I'll describe the circuit next up, and and I'll take you through the 3D printed components. So if we just plug that in again, you'll get a view what's going on from the inside, so to speak. And here we go. So it's rotating around. This Hall effect sensor is looking for the magnet. And you can see it's finding magnets at the moment. Here comes magnet now. And as soon as it goes past that magnet, so you can see it's now changed to calculating steps per revolution. So we're looking for the magnet again. I might just do a little change onto the script to calibrate in both directions, which I think the original project had that, just in case there's a slight difference. I'm not sure if I detect a little bit of creep in one direction. If you go step to step, just keep going in that direction. But we do take the opportunity here, whenever this magnet goes past the Hall sensor, no matter how long you've been using it, from one filter to the other, whenever we go past the magnet, we take the opportunity to recalibrate it, because we now know in relation to everything else where that magnet is on the wheel, and if it goes past the magnet and it thinks it's at position 10, when it knows the magnet's at position 0, it'll reset itself to position 0. So it will recalibrate. And another little tweak I might do is to say, okay, let's do a maximum of five moves between filters without going past the magnet. You know, of course you might go past the magnet anyway, in which case that's fine. It reset your count. But if you're on your fourth move and you still haven't gone back past the magnet, maybe on the fifth one, force it to go past the magnet, even if that's the longer way to the filter, to make sure that it gets recalibrated every now and again. But yeah, how many moves are you going to do in a night as well anyway? Anyway, that's it. So what I'll do is I'll take you through the circuitry and the 3D design, and then we'll take a look at how we connect this up to a piece of astronomy software using an Ascom driver. I think the original driver, as I say, uh, emulated the ZWO communications commands through the wire. This one has its own custom written driver using the Ascom templates, and we can look at that in Visual Studio and see how that works, what methods we needed to implement, and then see it in action on a couple of different pieces of software. I've got this running with APT and Nina. There's no reason to suppose that it shouldn't work with other astronomy Ascom compliant astronomy software as well. So this is the circuit used to power the filter wheel. It's essentially, if not the same as the circuit from the original YouTube video I drew this from. We've got the Arduino ZWO microcontroller here, and we draw the 5 volts to power the circuit, most of the circuit. You'll see that the OLED screen here requires 3.3 volts, so we take that from the 3.3 volt pin from the Arduino there. The GPIO pins are set to 3.3 volts when they're high on this Arduino. And then we've got the AL293D motor driver here. That is powered by 5 volts at VCC1 here, which powers the chip itself. It then takes another voltage into VCC2, which is used to power the stepper motor itself through these outputs. So whenever an input pin is set high, so for instance here, input pin 4 from GPO5, then output 4 will supply the voltage to the pin 1 of the stepper motor. This is being run in bipolar mode, which means that we've not got the red wire connected. And reading about that, it would suggest that we need 10 volts minimum to drive this stepper motor, but all I can say is we're driving it here just from the 5 volts, and it works fine. We're not expecting a great deal out of it to drive that filter wheel, and I do have to set a delay in the script to a correct value. If it's too small, we try to drive the stepper motor too fast, it will stall. So we've got a couple of buttons here and some pull-up resistors, and we'll use the inputs from those buttons to drive some things in the script to tell the stepper motor to go forwards or backwards around the filter wheels. And we've got the OLED screen here to output some information to the user, and then over here we've got the Hall effect sensor to detect the magnet on the filter wheel. There's a capacitor here, which is to filter out noise, and that's about it. So all this is being put onto a donut board, I think they're called, and I'll put this VCAD diagram here up onto GitHub as well. I mean, look at it and weep. It's pretty tricky to see what's going on here because I've got components on both sides of the board. So, for instance, if I just take the net trace off here, if you can just see that red box here, that's the Arduino ZWO on the board. But you can also see the display, it appears to be in the same place. Let me just see if I can highlight the display. As you can see, it's quite tricky to get the there we go. So this is the LED display, and that's because that's mounted on the other side of the board. Um, I use this to try and lay out the components on the donut board. And if you are very careful and know what you're looking at, you can use this to see how things are wired up on the board. So here's the ground connections. Here are the ground connections. And if we look at this one, that's the 5 volt supply, and you can use this to see how things are connected up. I'll include it, but just be very careful how you use this so you really understand how, when you're wiring up on the board, how it relates to this circuit diagram here. It's a fairly simple circuit, so as you're putting things on the board, you should you should be able to see fairly clearly what needs to be connected up. That's about it. I mean, just to be clear on the driver, whenever one of these pins is high, as I say, um, input 3 here, set that high. It means that we then take the voltage from VC to VCC2, and it's output through 3. So input 3 high, uh, then output 3 is high. But it could be at a higher voltage. These things are designed to say take a signal voltage of 3.3 volts, and it could be 12 volts being supplied through VCC2. In our case, it's 5. So this is the 3D design for the case so you can 3D print that. I'll put this up as a Fusion 360 export, but there'll also be STL files for the 3 parts that you need to print. Now, this will work. This worked for what I put together, and you may find that for your particular circuit board, it's not quite right, and you may need to tweak it or just file some bits off or whatever, or try and do the board to fit. So what I did to begin with is to mock up the filter wheel itself. So if I take out all these other components, you can see here I've got the filter wheel of at roughly the right dimension. I've got as good as I could get. Most importantly, these holes here are the right distance apart, and the wheel here is the right distance. So I could start to build everything around this. I looked on the public sites for Fusion 360 objects and came across the model for the 28 BYG 48 stepper motor, so I didn't have to do that. I just imported it, and I positioned that so you can see in the right place, so that when we put a little wheel on top of that stepper motor, which we will print, where's the wheel? Here we go. That the wheel now is coming up against the wheel of the filter wheel. There'll be a rubber band around this driver wheel here, and then that in turn will be mounted on the bottom of the box, which is the main component. So if I put that bottom of the case in, and you can see there that let's bring this up. You can see that the stepper motor sits on a couple of platforms there. There's a bolt goes through this section here, and then there's a slot here, so you can just move that wheel in and out to get the right pressure against the filter wheel to drive it. There's a platform here to hold the Hall sensor. I've got a little tiny Bolivera board, so it sits on this ledge, and there's a little bit of a cutaway beneath it to accommodate the solder blobs on the bottom and the cut-off wires. And then the board itself sits on the top here. They've got a couple of lugs that fit through the holes in the donut board, and you can see the whole thing is secured on the filter wheel via these tabs which go across the top, through which you'll put screws directly into the filter wheel, and on the bottom it overlaps the filter wheel there. And there you can see where the bolts come through the bottom of the case. Um, I recessed the hole for the bolt here to take the head of the bolt, but I didn't here because it was a slot. If I put a recess, it was quite a big cutaway, so I left that so the head of that bolt will protrude, but the whole stepper motor protrudes anyway. So that's the bottom of the case. There's a hole there for the USB cable to plug in. There's a window there through the side of this wall for the cables to come through for the stepper motor and the Hall effect sensor. And then we have the board which sits on top. So I've got a mock-up of that. You can see the buttons there on the screen. And that just sits on top, and as you can see, the lugs from that bottom of the case just fit through the board there. And then on top of that, we then have a driver case top, and that just fits on there. And then we've got the bolts which will go through the top of the case, through the lugs on the bottom of the case, and then screw into the filter wheel. And then there's another bolt which goes through here just to secure the bottom and the bottom and top of the case. And you've got the window for the LED and the two holes there for the buttons. And that's it. So as I say, I'll put the Fusion 360 export files up on GitHub, and I'll also put the STL files for the components that you need to print, which are the top of the case, bottom of the case, and the wheel that sits on the stepper motor. As I say, that fits the board that I put together for this. You may not fit yours, so you may want to come in and tweak this a bit, or try and get the board exactly the same dimensions as mine. Okay, we're going to talk about the software used to drive the filter wheel and to implement the Ascom driver so that we can then manipulate this filter wheel via Astronomy software that's Ascom compliant. The hardware itself is driven by an Arduino script. I use the Arduino IDE here. There are other options available. There's a Visual Studio extension which I did download and install, but it took me so long to get round to having a play with it that I found the trial period had run out. So that I can't really say how good that is. And to be honest, for what I use it for, I suspect the IDE is the Arduino IDE is enough. There's also a product called Platform IO, which you can use with VS Code. I've uploaded 3 different scripts. There's a tester 2, who knows what happened to tester 1. There's a magnet locator and the main driver itself. So tester 2 will just drive the stepper motor a bit backwards and forwards, use the buttons, will detect a magnet with the Hall effect sensor and print a message to the screen. And it's really just to test that you've got things wired up correctly. Even if it's just on the breadboard, you can get things laid out on the breadboard and use the tester 2 script just to test for the basic functionality. One of the things I really had a bit of a job getting right was the driving of the stepper motor, and that will test that part of the development. And then there's a second script called FW Magnet Offset Calibrator. When you first convert this filter wheel, what you're going to do is take it apart. You're going to drill a hole in the rim and put a neodymium magnet in there. And where that magnet is, it will depend on how far or how many steps of the stepper motor you have to go to get to a filter wheel. And we don't know that. We need to, so we can locate where the magnet is from the Hall effect sensor, but we kind of have to calibrate our final script to say how far the filter is away from that magnet, because it could be anywhere. I chose to put the magnet in a place where you can't see it when there's a filter wheel in that eyepiece window. So if I load that script up, what it will do is it'll look for the magnet, and I should say that the text of the script is tiny because it uses the embedded fonts, I think, for the LED, and there are two sizes, tiny and big, and you can see here that is saying finding home in the tiny font. When I finish the final script, I use the Adafruit GFX library to use a slightly different font, which is big but slightly smaller than the big font that comes with the standard software for the LED. And you'll notice now that the filter wheel has found the magnet and it's saying ready pos 0. But the filter wheel itself is not in the window because all it's done is find where the magnet is. The magnet is now kind of under that Hall effect sensor. I actually determine, I think the right hand, and I know the right hand side of the magnet as the home position. So that boundary between the Hall effect sensor going from true to false on the right hand side of the magnet is my home position. So that's now at home. So I just use the buttons now to rotate the filter wheel in a clockwise direction until I think that I've got that kind of central in the window. And what I can see there now is that says 1217, I think it is. And I just record that and we use that to calibrate the main script. So if I then go back to the main script, I can see that we've got this defined filter pos, and you can see the last time I looked at this, I determined that was going to be 1110. That's the number of steps, so not quite what we just saw there, but you know, the steps are very tiny. So and I would take that as a starting point. You put that in, you run your final script, and if you feel that the filters just don't are not quite central, you can tweak that a bit. But that second script will give you an initial value to put into that to hopefully get the Arduino script calibrated. So if we now load up the main filter driver, what we'll do is to go through that calibration. So it'll look for the magnet, it'll then rotate 360 degrees to measure the steps per revolution, and then it'll move that number of steps that we just calculated to take it to an initial filter. And you can see the font now is bigger because we're using those Adafruit GFX libraries. So that's now calculating the steps of revolution. You can see I've actually got filters installed there. Later on, we can give those filters some names, and they won't, perhaps in a lot of cases, won't quite look what you think might be in there, depending on what angle the camera is pointing at them, because the coatings can be quite deceptive as to what the filter actually is. A blue filter will look red at a certain angle. Right, so that's now parked at filter 4. You'll notice, I think they went back to filter 4 rather than filter 0, and that was to ensure, and I could probably take that out, it was to ensure that if we recalibrated for any reason, that immediately that magnet is on the right-hand side of the Hall sensor, and we wouldn't have a long way to go to find it again. And I did that because when you connect from an Ascom device, it was causing a recalibration immediately every time I did this. And in fact, it wasn't specifically connecting. It was the first connect. So you could have several pieces of software connecting, and it was always the first one when the hardware kind of got initialized the first time. But I have found a way around that now to stop that happening. So if it's calibrated already, it won't immediately recalibrate when you plug it into a bit of Ascom. So I could set that to start off on filter 0, the first filter rather than the last filter, because we're not really protecting ourselves against a laborious recalibration now. Okay, so that's your Arduino script, and I'll just go through a little bit here. You can see that down here we've got some in the main loop, we're looking on the serial port for commands that end with hash and these could be get filter or filter, connect, calibrate. We shouldn't need to use that calibrate, or I think the Ascom one I do call that, but it doesn't really do anything. Again, it was all part of this trying to get the calibration right in the first instance. And if we've already calibrated, as we've just done now, just by powering it up, that calibrate method won't do anything because it'll detect that it's already calibrated and just immediately return OK. If it knows it's not been calibrated for any reason, then it will go and calibrate. And yeah, so that's it. It's a very simple serial interface there. There's very few commands that you can do. I mean, there's not a lot to a filter wheel. You can tell it to connect, disconnect, or go to a particular filter. Okay, so if we now go to the Ascom side of things, this was all developed in Visual Studio. And I used a package extension called Ascom Platform 7 Project Templates. And what this will do for you is to create you a template driver for any particular device. So if we go to, let's kick one off. So if we say new project, and then we say Ascom in here, then we can see we've got this platform driver here. So if we double click that, and what you want to do is just get this right, these names here right, because it depends. Yeah, what will go into your what will appear in Ascom will depend on that. And I had fun and games with that a little bit, but let's say filter 2. I don't know, filter 2. And I would suggest just building one, loading it to Ascom and understanding where the name appears. Right, create. And then we've got what type of device you want to create a driver for. So filter wheel, vendor or organization. So I've called mine Astro. And device, I don't know, FW2. And create. And it will create a project. And what you'll get also is this page here, and it gives you some good information about how to implement this project. There's a load of information on the Ascom site, and I really, if you're going to do this rather than just take the one that I've done, which I'll show you in a second, I'd really start reading up on this, particularly with the Platform 7, which has got an asynchronous interface to the drivers, which means that multiple bits of software can be calling it, and you just need to understand the way that works. Most of the complexity is hidden from you. There's not a lot you need to do, which I'll show you in a second. Yeah, and also in this this bit here, which I think I'll put a link to on the GitHub, you can see how to install the driver after you've developed it. And it's down this bit here. Here we go. So run the local, because what this will do when you've implemented your driver, you'll have an executable, a local server executable, they call it. I think there we go, local server executable, and you need to run that with this reg server parameter, which registers it with Ascom, and then you'll see your driver appear in the chooser. So I'm going to get rid of that, and we're going to go back to the original one that I've developed. Okay, so here's one I did earlier, and what you'll find if you read the documentation is that the main bit you've got to alter is this class here, which is filter hardware C# file. And in there are a number of things you're interested in. First of all, there is a initialize. and you're going to put some little bits and pieces in there, or I put some bits and pieces in there. This is connecting to the serial port. I've set the board speed there. I've also got this DTR enable equals false here, and I was talking before about when I initialized the hardware in Ascom, I found it was recalibrating, which was a pain. I found the magnet. I've gone 360 degrees round the wheel, and then I'm doing it all again as soon as I connect to Ascom. And if you set this line, the DTR line, to false, then you stop that happening. And I've got a timeout of 90 seconds. Well, that's 90 seconds. That was to accommodate the initial calibration. We could probably drop that now, actually. And then I call calibrate, but that now just returns true. So unless it's uncalibrated, then it'll reply straight away. And then you see we drop that timeout down to 10 because now we expect the command uh, to return within 10 seconds, which is a value I just determined from looking at what's the lengthiest thing I do, which is to go from one filter to another where they're two apart, because we're never going to move more than two positions. We move clockwise or anti-clockwise depending on what the shortest rate is. So the lengthiest thing you're going to do on this filter wheel is to move between two filters, or move two filters along, I should say. What else did I do? Well, there is the serial command, which I put in there to actually send the commands to the filter wheel. And in that, I've put a serial port lock because, as I say, in theory, the way this is implemented, you can have multiple bits of Ascom software communicating with the filter wheel, and this just stops you trying to tell the filter wheel to do two things at once. Now, if you tell it to go to filter 2 from filter 4 and then unlock it, you may find another bit of software would tell it to go somewhere else again. But I mean, then you've got something else wrong. Your setup. You've got multiple things telling a filter wheel to go in different directions. But yeah, I've put the lock in there anyway to protect that. Right, so there's not a lot else to do. I mean, there are things like position. And what I do here is I say, call that serial command depending on the position that's been entered, and just tell it to go to filter whatever with a hash index. Now the filters have actually got names within this class, and we translate this into the index number of that name in the array, and tell the filter wheel to go to filter 0, 1, 2, 3, or 4 depending on where we are in that array. Where are they? We've got just looking for the filter wheel names. They are here somewhere, but by default they're filter 0 to 4. But once you've invoked this, then you'll populate the Ascom profile for this driver, and then you'll get some names. Now, how do we do that? Right. Okay. So, I should say while we're on here, the other one that we have done a little bit is in Connect, but there's not a lot in there. What I would do is, if you're really interested in what I've written in this class, is to create yourself a template, a filter wheel template, and just compare this filter wheel hardware CS to what you get out of the template generator, and you'll see there's not a lot of stuff in here. Right, so when you initialize this, it will also initialize the dialog form, and in the dialog form, which is what you'll see when you connect to a filter wheel in the first instance, we've got these values here. And I think when you generate this from the template generator, all you get is the COM port and trace on OK and cancel, and that's it. So I've added these 5 other boxes which enable you to name your filters. And when you do that, where are we? That's the designer. We don't want the designer. We want this one. When you do that, you'll store the values and you'll set those into the array that's in the hardware C#. I'm just trying to get the where are we? Open with C# editor. There. Right. Oh, here we go. So when it pops up in the first instance, this is the init UI. So this is when that dialog box pops up. It sets the values in those boxes to whatever's in fnames, which is the array in the driver. And by default, if you've not done anything with it before, it'll be filter 0, filter 1, 2, and 3, and 4. And when you later save it, you press OK, you'll see it does the opposite. It says, OK, now you've finished with the dialogue, and you may have altered those values, and we're going to set fnames in the hardware C# module to the values in the text boxes. And also, when you press OK, under the covers, that will feed back into the filter wheel hardware module, and it will save those to the Ascom profile. So that will persist from one iteration to another. Now, as I say, have a look at all that code. That's about it, and let's go and use it. Okay, so let's look at how all that fits together and demo it in some astronomy software using Ascom. So first of all, I'm going to install the driver. And I've got the Inno installer here. As I say, you can build the project yourself and register your own executable, but this is bundled up and we'll do it for you. So we execute that. We'll get the warning about it being publisher unknown. And there's our license agreement to accept. And the install is pretty quick. It doesn't really do very much at all. And finish that, and it takes you to a web page, which will take you in turn to the GitHub page describing this project. I mentioned earlier on about the filter names, by the default filter names. I did find it there, and you can see that they're not filter 0 to 4. By default, in the software, they come out as red, green, blue, clear, and other. This is kind of your default if you've not changed anything. So now we'll start some piece of software. We'll use NINA. That's Nighttime Imaging in Astronomy. And here's Nina. There are the different pieces of astronomy software have idiosyncrasies, one of which is that Nina will store the filter names in its own offline storage. And so if you change the filter names in Ascom, they will be ignored if Nina has already got its own filter names. It'll just use those instead. So although we've installed this filter driver afresh, I have been using Nina to test out earlier. So I suspect if I go in here, there are some filter wheel names that it's remembering. So I'm going to get rid of all of those. And then we come back to equipment. And first of all, if we click filter wheel, you can see that here is our filter wheel in the Ascom list. By installing it, it now knows where it is, and it's registered to Ascom, so appears in this chooser section for filter wheels, along with a number of other ones you just get out of the box with the Ascom platform. So we've got the Ascom filter wheel driver for Foggy Astro filter wheel, and we'll select that one and connect. And what we'll should get is a success message, which we have. It's on the other screen, of course, which I don't seem to have me move. You'll take my word for that. That's succeeded. Right, you can see it here anyway. So if I now pull down, I've got a list of names, and that red, green, blue, clear, and other is what we had in the software itself. And so we know that it also knows it's got from the filter wheel what filter it's on at the moment, because I happen to be parked on green on the filter wheel, if you can see down there in the bottom right hand corner. And from Nina I can now choose another one. So let's go back to red, and you can see the filter wheel going back, and it's saying green to red, and when it's finished, parked red bracket 0, so filter position 0, which is red. And let's just remind ourselves again, we've got red, green, blue, clear, and other. So we might decide that we want some different names. So if we disconnect from the filter wheel and then go into the profile, up pops that dialog box which we saw in the Visual Studio project, and in here it's been populated with the defaults from the program, and we can change these. Now there's a limit of 8 characters because of the length of text we can put on that LED screen on the filter wheel, and that's that limit is in this dialog. Right, so I'm going to call this one Loom IR, and this one IR UV. So we've just changed those. Okay, and don't forget in Nina, it's saved the names it knows about already. So we're going to go into that. If I don't do this, then we're not going to see those new names appear. So I'm just going to clear those out again. Just the way Nina does things. It does it for a reason. I can't remember the precise reason, but you can find out if you're interested. Right, so now I've reconnected, and if I pull down that list, sure enough, we've now got red, green, blue, Loom IR, and IR UV. We're on red, and if we go to Loom IR, you can see the filter wheel's now saying red to Loom IR. And park Loom IR on position 3. That's it, really. So that's as much as we need to know about Nina. So let's disconnect and try another piece of software. So we've saved that those filter names, and by doing that, it's saved it in the Ascom profile. So if we start up APT or any other bit of software that uses filter wheels, then we should see the names we save in the profile. Unless, of course, it behaves the same way as Nina and decides not to use that position. Now I'm going to have to just move this to the other parts of the screen, because in APT, what I'm going to show you is down here. So we'll go to our gear tab, connect wheel, and interestingly, you see that it says Loom IR red. I should have said, you'll notice when I said connect wheel, it just connected to it straight away. It didn't give me that chooser. Let's go back. If I right click, I then get the Ascom chooser, a different way of interfacing with the chooser. So I can say here, that's the one I want, and you can go into the properties from there should you wish. Right, so I'm going to connect the wheel. Oops. Right, okay. And yes, you'll have noticed when we connected, it also moved the wheel to the red filter. That's just the way that APT does it. If you connect to the wheel, it goes to filter position 0, which in our case is the red filter. But from here, we can pull up the list, and we've got red, green, blue, Loom IR, IR UV, which have been got from the Ascom profile, and we can just select one of those. Let's just go one on, and there you can see red to green, and round the wheel goes to green. And there's APT interacting nicely with the filter wheel as well. What you can also see, should you wish, is to look at the Ascom. There is a tool called the Ascom Profile Explorer, and in there, if you're interested, you can see the profile. So here's the filter wheel, and there's the foggy astro filter wheel, and there you've got the values that we set to those filter names, and you can, if you wish, change those filter names as well from this. Why you'd want to, I don't know. You might as well do it from the Ascom software probably. If you do uninstall the filter wheel, that profile will persist. It'll be offered up to Astronomy software and it'll fail to connect, in my experience, because the program isn't there. Yes. So you may wish, if you really wanted to clear it out, come into this Profile Explorer and get rid of it. So that's about it. As I say, when you install the driver, it will point you to the GitHub site, and this is where I've uploaded all the files for this project. So we've got the main project here, which has got uh, get rid of that, which has got the the design for the case. It's got the circuit diagram here. We've got files for TinyCAD and a netlist and VCAD layout, which is a little tricky to use. We've got the main components used in that circuit, and then we've got the Fusion 360 design. But we've got the STL files if you just want to print those out, and they're suitable for the board that you're installing. And then we've also got the Fusion 360 export should you want to go in and alter that Fusion 360 design yourself. Inevitably, when I finished that design, there was a fair bit of tweaking at the end. I just kind of pushed this wall this way a bit, or I'll move this slightly to the side. So there's quite a few little tweaks at the end of that design. And then you've got a link to another project. Now, this is the Visual Studio project. It used the GitHub interface in Visual Studio to save this repo. So you can load this straight into Visual Studio. It's got all the stuff for the Ascom driver itself, and it's got these two extra directories where we've got the we've got the Arduino scripts, the filter wheel firmware, and we've got the Inno installer here in this one. But if you take the view in Visual Studio of just the project, which I think we were on there, you won't see those. So I'm in the project view, or Solution Explorer rather, and you won't see them. It's only if you go to folder view that you can see those additional folders. But what it does mean is that if I alter anything in the Arduino firmware or the installer, it gets picked up by by GitHub in Visual Studio. Just make my life a little bit easier doing it that way. And that's it. I hope that if you are considering converting one of these filter wheels from manual to electronic, this will give you something to go on. I took my inspiration from that YouTube video. I hope this will. This is my interpretation of it, and I hope that the files that are provided here will give you a starting point at least if you want to do the same thing yourself. And if you do, then I wish you luck and enjoy yourself having a go with it. If you do change anything with the driver code, then I'd be happy to have a look at that and integrate it into mine. If you want to come up with some fancier GUI on the driver wheel, then I'd be very interested to see it. And you can put a pull request if you want, and I can take a look at that. Okay, have fun.